It was a normal Friday morning in Chelyabinsk, Russia. February 15, 2013. Commuters drove to work under clear winter skies. Students filed into classrooms. Office workers grabbed their morning coffee. Nobody knew that hurtling toward them at over 60,000 kilometers per hour was a 20-meter-wide asteroid that was about to explode over their city with the force of 30 Hiroshima bombs. At 9:20 a.m. local time, dashcams across the city captured what looked like a second sun blazing across the sky. The superbolide, as astronomers would later call it, lit up the morning brighter than daylight, casting stark shadows and turning the winter landscape into an alien scene of orange and white brilliance. For those first few seconds, people stopped their cars and stared upward in awe. Some thought it was a plane crash. Others wondered if it was a missile. A few even thought they were witnessing the end of the world. Then, roughly 30 kilometers above the ground, the asteroid disintegrated in a massive explosion that released approximately 500 kilotons of energy. The shockwave that followed shattered windows across 6 cities. Over 7,000 buildings were damaged. Glass rained down on streets filled with people who had rushed to windows to see what the strange light was. More than 1,500 people were injured, mostly from flying glass and debris. A zinc factory partially collapsed. And here's the terrifying part, the part that should make every person on Earth pay attention. We never saw it coming. Not a single telescope, not one space agency, not any of the sophisticated detection systems we've built to watch the skies detected this asteroid before it slammed into our atmosphere. It approached from the direction of the sun, effectively invisible to our ground-based observatories. The first time humanity knew about this asteroid was when it exploded over a city of 1.1 million people. If it had been just slightly larger, if it had exploded at a lower altitude, if it had hit a more densely populated area, we could have been looking at tens of thousands of casualties instead of injuries. And the truly sobering reality is this: there are thousands, perhaps tens of thousands of asteroids like it out there that we haven't found yet. Objects that could appear tomorrow, next week, or next year, giving us zero warning before impact. Welcome to the uncomfortable truth about asteroid threats. We like to think we have this figured out. We've seen the movies where heroic astronauts blow up the asteroid at the last second. We've heard about NASA's planetary defense efforts. We assume that if something dangerous was heading our way, someone would tell us, that we'd have time to prepare or evacuate or do something. But the reality is far more complex and far more unsettling than Hollywood would have you believe. Right now, at this very moment, there are asteroids out there with Earth's name on them. Some we know about. Most we don't. And the ones we should worry about aren't necessarily the giant civilization-ending rocks that make headlines. Those, ironically, are the ones we've mostly found. It's the smaller ones, the city killers and regional devastators, the asteroids that could wipe out millions of people but leave the rest of humanity intact to witness the horror. Those are the ones that keep astronomers awake at night. Let's start with what we actually know, and more importantly, what we don't know. NASA and other space agencies have been conducting comprehensive surveys of near-Earth asteroids for decades now. The progress has been remarkable. As of 2024, we've discovered and cataloged over 35,000 near-Earth objects, or NEOs. These are asteroids and comets whose orbits bring them within 195 million kilometers of the Sun, which means their paths cross Earth's orbital neighborhood. We've gotten very good at finding the big ones. NASA estimates that we've now detected approximately 95% of near-Earth asteroids larger than 1 kilometer in diameter. These are the planet killers, the objects that if they hit Earth would cause global catastrophe, mass extinction, the end of civilization as we know it. Finding 95% of them is genuinely impressive and represents decades of systematic observation and increasingly sophisticated detection technology. But here's where the comfort ends and the worry begins. When we move down to the next size category, asteroids larger than 140 meters in diameter, our detection rate drops dramatically. These aren't planet killers, but they're absolutely civilization scarring. An asteroid 140 meters across hitting Earth would release energy equivalent to hundreds of megatons of TNT. If it hit a major metropolitan area, it would obliterate the entire city and surrounding region. If it hit an ocean, it could generate devastating tsunamis that would strike coastlines thousands of kilometers away. These are regional catastrophe objects, capable of killing millions of people and causing trillions of dollars in damage. Current estimates suggest there are approximately 25,000 near-Earth asteroids larger than 140 meters. We've found about 10,000 of them. That means roughly 15,000 asteroids large enough to cause regional or continental devastation are out there, orbiting through our cosmic neighborhood, and we have no idea where they are. The detection rate is even worse for smaller objects. For asteroids in the 30 to 50 meter range, objects comparable to the Chelyabinsk meteor or the asteroid that caused the famous Tunguska explosion in Siberia in 1908, we've probably detected less than 10% of them. There could be hundreds of thousands of these objects, and we're essentially flying blind. Every single day, Earth is playing a cosmic lottery, and we don't even know most of the numbers that could come up. Now, you might be wondering why this is so difficult. We can see galaxies billions of light years away. We can detect exoplanets orbiting distant stars. Why can't we see a rock that's only a few million kilometers away? The answer comes down to several frustrating factors that make asteroid detection far more challenging than most people realize. First, asteroids are small. Even a 1-kilometer asteroid, a civilization-ending threat, is absolutely tiny on cosmic scales. These objects don't emit their own light. They're only visible because they reflect sunlight, and they don't reflect much of it. Most asteroids are made of dark, carbon-rich material that reflects only about 3 to 5% of the light that hits them. They're basically cosmic coal, black rocks tumbling through the blackness of space. Trying to spot them against the star-filled background of space is like trying to find a particular grain of black sand on a beach at night using only a flashlight from 100 meters away. Second, we're looking for them from a moving platform. Earth is orbiting the Sun at about 30 kilometers per second, and the asteroids we're trying to detect are also moving in their own orbits at varying speeds and directions. Determining whether an asteroid is actually on a collision course with Earth requires multiple observations over time to calculate its precise orbit. A single observation isn't enough. We need to track these objects, measure their positions carefully, and do complex mathematical modeling to figure out where they're going to be months or years in the future. This takes time, and time is something we might not have if we only spot an asteroid when it's already close to Earth. Third, and this is perhaps the most troubling limitation, we have a massive blind spot. Most asteroid surveys are conducted using ground-based telescopes, which means they can only observe at night and only when weather permits. More critically, these telescopes cannot look in the direction of the Sun. There's a huge region of space, a cone roughly 90 degrees wide centered on the Sun, where ground-based telescopes simply cannot observe. Asteroids approaching Earth from this solar exclusion zone are effectively invisible until they emerge from the glare, and by then, it might be too late to do anything about them. The Chelyabinsk meteor came from exactly this blind spot, which is why nobody saw it coming. Current surveys only cover about 60 to 70% of the sky on any given night, leaving vast regions unmonitored. An asteroid could be weeks away from Earth impact, and if it's approaching from the wrong angle, we might not know about it until days before it arrives or, as in the case of Chelyabinsk, not until it's actually exploding in our atmosphere. This brings us to one of the asteroids that genuinely frightened the scientific community when it was first discovered, 99942 Apophis. Named after the ancient Egyptian spirit of chaos and destruction, Apophis is a near-Earth asteroid approximately 370 meters in diameter. That makes it large enough to cause continental-scale devastation if it were to impact Earth. When it was discovered on June 19, 2004, by astronomers at the Kitt Peak National Observatory, initial orbital calculations suggested something absolutely terrifying. There was a chance, a real, non-negligible chance, that this asteroid would hit Earth on April 13, 2029. As more observations came in over the following months, the calculated impact probability actually increased. By December 2004, Apophis briefly reached a level 4 on the Torino Impact Hazard Scale, the highest level ever reached by any asteroid in the history of that scale. A level 4 indicates a close encounter that merits attention by astronomers, with at least a 1% chance of collision capable of regional devastation. At its peak, Apophis had an estimated 2.7% chance of impacting Earth in 2029. That might not sound like much, but imagine if meteorologists told you there was a 2.7% chance that a hurricane Category 10, something that doesn't even exist on our current scale, would hit your city next week. You'd probably start paying attention. The scientific community certainly did. Emergency meetings were convened. Papers were rushed through peer review. Space agencies around the world began discussing potential mitigation strategies. The media inevitably ran with headlines about the Apocalypse asteroid. And all the while, astronomers kept observing, kept refining their calculations, kept hoping the numbers would change. And fortunately, they did. As more data came in, as the orbital calculations became more precise, the predicted impact probability for 2029 began to decrease. By August 2006, the chance of a 2029 impact had been ruled out entirely. Refined observations, including radar measurements from the Arecibo Observatory and optical observations from telescopes around the world, allowed astronomers to calculate Apophis's orbit with sufficient precision to conclusively determine that it would miss Earth in 2029. But here's the thing, it's going to be a very close miss. On April 13, 2029, Apophis will pass within approximately 31,000 kilometers of Earth's surface. To put that in perspective, that's closer than the orbit of our geostationary satellites. This is a 370-meter-wide asteroid, large enough to see with the naked eye as it streaks across the sky, passing between Earth and our own satellites. It will be the closest approach of an asteroid this large that we know about in recorded history. For a few hours, Apophis will be visible to observers in Europe, Africa, and Western Asia as a magnitude 3 point of light moving rapidly across the sky. It will be a spectacular and unsettling reminder of how close these objects can come. But the story of Apophis doesn't end in 2029. That close encounter with Earth is going to change the asteroid's orbit. Earth's gravity will tug on Apophis as it passes, altering its trajectory in ways that are difficult to predict with absolute precision. For years after the 2029 flyby was confirmed to be safe, there remained concern about a potential impact in 2036. The scenario went like this. If Apophis passed through a very specific region of space during the 2029 flyby, a region astronomers call a gravitational keyhole, Earth's gravity could alter its orbit in just the right way to set up a collision 7 years later in 2036. A gravitational keyhole is a tiny region of space, sometimes only a few hundred meters across, where an asteroid's trajectory can be altered by Earth's gravity in such a way that it returns on a collision course on a subsequent orbit. Think of it like a cosmic bank shot in billiards. The gravitational keyhole for Apophis in 2029 that could lead to a 2036 impact was estimated to be about 600 meters wide. If Apophis's center of mass passed through this specific 600-meter-wide region of space during its 2029 approach, it would return to hit Earth in 2036. The initial calculated probability of passing through this keyhole was low, but not zero. Once again, the scientific community held its breath while observations continued. And once again, improved observations and calculations brought good news. By 2013, new data from optical and radar observations allowed astronomers to rule out the 2036 impact scenario entirely. The refined orbit showed that Apophis would not pass through the gravitational keyhole in 2029, meaning the 2036 threat was eliminated. Further observations have also ruled out any potential impacts for at least the next 100 years. Apophis is no longer considered a threat to Earth, at least not in any time frame we can currently calculate with confidence. But the Apophis scare taught us several important lessons. First, it demonstrated that our initial orbital calculations for newly discovered asteroids can be quite uncertain, and impact probabilities can change dramatically as we gather more data. Second, it showed that close approaches to Earth, even ones that don't result in impact, can significantly alter an asteroid's future orbit, creating new potential impact opportunities down the road. And third, it revealed just how much public attention and concern a potential asteroid impact can generate, which has implications for how space agencies communicate about these threats in the future. Apophis will forever be a reminder that we need to keep watching the skies, because the next asteroid that causes a scare might not turn out to be harmless. While Apophis was grabbing headlines for over a decade, another asteroid was quietly demonstrating just how easily these objects can slip past our defenses. On July 13, 2023, an asteroid designated 2023 NT1 made a close approach to Earth, passing within approximately 60,000 kilometers of our planet. That's about 1/6 the distance to the Moon, well within the orbital radius of many satellites. The asteroid was estimated to be between 50 and 60 meters in diameter, large enough to cause significant regional damage if it had impacted Earth. An object this size entering the atmosphere would likely survive to reach the ground largely intact, creating an explosion in the tens of megatons range. If it had hit a populated area, we'd be looking at casualties potentially in the hundreds of thousands. Here's the terrifying part. 2023 NT1 wasn't discovered until 2 days after it made its closest approach to Earth. 2 days after it had already passed us by, after the danger had already come and gone, astronomers finally spotted it. The asteroid had approached from the direction of the Sun in our blind spot, completely undetected by our survey systems. It was only discovered on July 15th by the Asteroid Terrestrial Impact Last Alert System telescope in South Africa, after the asteroid had moved far enough away from the Sun's glare to become visible. This near-miss received relatively little media attention compared to Apophis, probably because it was discovered after the fact, after the danger had passed. There's something less dramatic about reporting an asteroid flyby that already happened compared to one that's approaching. But in many ways, 2023 NT1 is more significant than Apophis as a wake-up call. Apophis was discovered years before its closest approach, giving us plenty of time to refine our calculations and rule out impact. 2023 NT1 demonstrated that a city-killer asteroid can approach Earth completely undetected, and we only find out about it after it's already gone past us. If 2023 NT1 had been on a collision course with Earth instead of a flyby trajectory, if its orbit had been just slightly different, the first warning we would have received would have been the explosion as it entered the atmosphere. There would have been no time to evacuate cities, no time to prepare emergency services, no time to do anything except watch it happen. This isn't a hypothetical scenario. This is exactly what happened with the Chelyabinsk meteor in 2013. The only reason 2023 NT1 didn't cause a similar event is luck. Its orbit happened to miss us. Next time, we might not be so lucky. And this brings us to perhaps the most concerning asteroid currently on our watch list. US 9955 Bennu. If you follow space news at all, you've probably heard of Bennu. It's been the target of NASA's OSIRIS-REx mission, which successfully collected samples from the asteroid's surface in 2020 and returned them to Earth in September 2023. The sample return was a spectacular success for planetary science, giving us pristine material from the early solar system to study in laboratories. But OSIRIS-REx wasn't just sent to Bennu for scientific curiosity. Bennu was chosen as a target in part because it's one of the most potentially hazardous asteroids we know about. Bennu is a carbonaceous asteroid, meaning it's rich in carbon and organic compounds, with a diameter of approximately 490 meters. It's what astronomers call an Apollo asteroid, an Earth-crossing asteroid whose orbit brings it close to Earth at regular intervals. Bennu approaches Earth every 6 years, though most of these approaches are at safe distances. The asteroid's orbit is very well characterized now, thanks to decades of ground-based observations and the close-up data from OSIRIS-REx, and what that data tells us is troubling. Bennu has a small but real chance of impacting Earth in the late 22nd century. The most significant risk comes from a close approach on September 24, 2182. Current calculations give Bennu a cumulative impact probability of approximately 1 in 2,700, or about 0.037%, across multiple possible impact dates between 2178 and 2290. That might sound like comfortably long odds, but consider what we're talking about. A 490-meter asteroid impacting Earth would release energy equivalent to approximately 400 megatons of TNT. For comparison, the largest nuclear weapon ever tested, the Soviet Tsar Bomba, yielded 50 megatons. A Bennu impact would be like detonating 28 Tsar Bombas simultaneously. If Bennu hit land, it would create a crater roughly 10 kilometers in diameter and cause continent-scale devastation. The immediate blast effects would obliterate everything within hundreds of kilometers. The seismic shaking would trigger earthquakes across tectonic plate boundaries. Ejected material would rain down across thousands of kilometers, starting fires and causing secondary impacts. And the dust and debris thrown into the atmosphere would likely trigger years of climatic disruption, leading to global crop failures and potential famine affecting billions of people. If Bennu hit an ocean, the immediate crater effects would be less severe, but the tsunami generated would be catastrophic. Models suggest that a 490-meter asteroid impacting the Atlantic Ocean could generate waves over 100 meters tall that would strike coastlines on both sides of the ocean within hours. Every coastal city from Boston to Miami, from London to Lagos, would be inundated. The death toll could easily reach into the hundreds of millions. Now, 1 in 2,700 odds might seem acceptable. After all, you're more likely to be struck by lightning in your lifetime than Earth is to be hit by Bennu on any given close approach. But here's the thing. We're not talking about your individual lifetime. We're talking about civilization-scale risks. A 0.03% chance of an event that could kill billions of people and collapse global civilization is not a risk we can simply shrug off. If I told you there was a 0.037% chance your house would burn down tomorrow, you probably wouldn't worry too much. But if I told you there was a 0.037% chance that every house in your country would burn down simultaneously, you'd probably want someone to do something about that. And the situation with Bennu is complicated by something that happened in 2135. On September 25, 2135, Bennu will make an extremely close approach to Earth, passing within about 300,000 kilometers, roughly 75% of the distance to the Moon. This close encounter will significantly alter Bennu's orbit through gravitational interaction with Earth. The exact change in the orbit depends on extremely precise details of how close Bennu comes and the exact geometry of the encounter. Small differences in Bennu's position during the 2135 flyby, differences measured in kilometers will result in vastly different trajectories afterward. This is where those gravitational keyholes come into play. Depending on exactly where Bennu is during the 21 to 35 approach, Earth's gravity could nudge it into an orbit that brings it back for a potential impact in 2182 or 2196, or any of several dozen other possible dates through the end of the 23rd century. The current impact probability calculations are based on our best understanding of Bennu's orbit as of now, but there are uncertainties. We know where Bennu is quite precisely, thanks to OSIRIS-REx, but predicting exactly where it will be in 2135 and how the Earth flyby will affect it requires accounting for numerous factors. These include the Yarkovsky effect, a subtle but important force that affects asteroid orbits. The Yarkovsky effect occurs because asteroids absorb sunlight and then radiate that energy away as heat, but they don't radiate uniformly. The side of the asteroid that's rotating away from the Sun, the afternoon side, if you think of the asteroid as having a day-night cycle, is warmer than the side rotating toward the Sun. This temperature difference creates a tiny thermal thrust that can slowly change the asteroid's orbit over time. For something as massive as Bennu, the Yarkovsky effect produces acceleration measured in fractions of a millimeter per second, but over decades and centuries, this adds up. The OSIRIS-REx mission specifically measured how the Yarkovsky effect is influencing Bennu, improving our predictions of its future orbit. Without accounting for the Yarkovsky effect, our predictions for Bennu's position in 2182 would be off by hundreds of thousands of kilometers. With the OSIRIS-REx data, we've significantly improved our orbit predictions, but uncertainties still remain. The good news, if we can call it that, is that we have over a century to refine our calculations, and if necessary, to develop and implement a deflection mission. Unlike the scenario of an asteroid discovered only months or years before impact, Bennu gives us time. We can continue to observe it, improve our orbital models, and watch how the 2135 encounter actually affects its trajectory. And if the post-2135 orbit looks dangerous, if it becomes clear that Bennu is heading for one of those gravitational keyholes that would set up a 2182 impact, we'll have decades to plan and execute a deflection mission. But here's the question that should concern us. If Bennu, an asteroid we've studied extensively, that we've sent a spacecraft to, that we've collected samples from, still has a 1 in 2,700 chance of hitting us, what about all the asteroids we haven't found yet? What about the thousands of Bennu-sized objects that are out there in near-Earth space that we've never detected? This is where the statistics become truly sobering. Our current survey completeness, that 40% figure for asteroids larger than 140 meters, isn't evenly distributed across all types of near-Earth asteroids. Some orbital types are much harder to detect than others. Near-Earth asteroids are generally classified into several groups based on their orbits. Itons are asteroids whose orbits lie primarily inside Earth's orbit. They spend most of their time closer to the Sun than Earth is, which makes them extremely difficult to observe from our vantage point. We've probably only detected a small fraction of Iton asteroids. Apollos, like Bennu, have orbits that cross Earth's orbit and spend time both inside and outside Earth's orbital path. These are somewhat easier to detect because they spend part of their orbit in the outer solar system, where ground-based telescopes can see them against the dark sky. Amers have orbits that lie just outside Earth's orbit. They approach Earth closely, but don't actually cross our orbital path. These are generally the easiest to detect because they're often well-positioned for observation. And finally, Asteroids are asteroids whose orbits lie entirely inside Earth's orbit. They never venture into the outer solar system, spending their entire orbits between the Sun and Earth. These are extraordinarily difficult to detect because they're always located in the direction of the Sun from our perspective. We've only discovered about 30 Asteroids asteroids so far, but models suggest there could be thousands of them. Each of these populations presents different detection challenges, and our survey completeness varies dramatically between them. We've probably found most of the large Amors. We've found a decent fraction of the Apollos. But the Atens, and especially the Asteroids, remain largely unknown. And here's the truly frustrating part. Asteroids that spend most of their time close to the Sun, the Atens and Asteroids, are actually more likely to hit Earth than asteroids in other orbits. This is simple orbital mechanics. Objects with orbits similar to Earth's orbit have more frequent opportunities to intersect with Earth, and their relative velocities when they do intersect tend to be lower, which actually increases the collision probability. It's counterintuitive, but a slower-moving asteroid in an Earth-like orbit is more dangerous in terms of collision probability than a faster-moving asteroid in a very different orbit. So, the asteroids we're worst at detecting are also, in some sense, the most likely to hit us. This is not a comforting realization. The fundamental problem we face is that our asteroid detection infrastructure was designed and built with certain assumptions and limitations that made sense when the programs were started, but that increasingly look inadequate as we understand more about the threat. The overwhelming majority of asteroid surveys use ground-based optical telescopes. These telescopes scan the night sky, taking multiple images of the same region separated by minutes or hours, and then use computer software to identify objects that moved between images. Anything that moves is potentially an asteroid. The motion tells you it's not a star or galaxy. Further observations over subsequent nights allow you to calculate the object's orbit and determine if it's a near-Earth asteroid, a main belt asteroid, or something else entirely. This technique works, and it's responsible for the vast majority of asteroid discoveries over the past 3 decades, but it has inherent limitations that we cannot overcome without fundamentally changing our approach. Ground-based telescopes can only observe at night. This immediately cuts your observing time in half. They can only observe when weather permits, which, depending on location, might eliminate another 30 to 50% of potential observing time. They can only observe objects above the horizon, which means from any given location on Earth, you can only see roughly half the sky at any given time. And most critically, they cannot observe in the direction of the Sun. All of this adds up to ground-based surveys being able to observe maybe 20 to 30% of the sky on any given 24-hour period. The other 70 to 80% remains unmonitored. An asteroid approaching Earth from the wrong direction could be weeks away and remain completely invisible to our detection systems. We saw this with Chelyabinsk. We saw it with 20 NT1. And we'll see it again with the next asteroid that happens to approach from our blind spot. There's another problem with ground-based optical surveys. They're biased toward detecting certain types of asteroids. Bright asteroids, those with high albedo that reflect a lot of sunlight, are much easier to detect than dark asteroids. An asteroid that reflects 50% of incident light, which would make it exceptionally bright for an asteroid, can be detected at much greater distances than an asteroid that reflects only 3% of light. But most asteroids, particularly the carbonaceous ones like Bennu, have very low albedos. They're dark, sometimes nearly black. This means we're systematically better at detecting the less common bright asteroids, and worse at detecting the more common dark asteroids. We are selecting for visibility rather than true abundance or danger. Size also matters tremendously. The brightness of an asteroid depends on both its albedo and its size. A small bright asteroid might appear just as bright as a larger dark asteroid at the same distance. Without additional information, you can't tell from brightness alone whether you're looking at a small bright rock or a large dark rock. This requires follow-up observations, sometimes including radar measurements or infrared observations, to determine the asteroid's actual size. And all of this takes time and resources. For decades, The workhorse of asteroid detection from space has been the NEO mission. NEO, which stands for Near-Earth Object Wide Field Infrared Survey Explorer, was originally launched in 2009 as WISE, a mission to conduct an all-sky survey in infrared wavelengths. After completing its primary mission, the spacecraft was brought out of hibernation in 2013 and repurposed for asteroid hunting. NEO operated in infrared wavelengths, specifically looking at heat rather than reflected visible light. This gave it a crucial advantage over ground-based optical surveys. In the infrared, an asteroid's brightness depends primarily on its size and temperature, not on its albedo. A large, dark asteroid and a small, bright asteroid that might look similar in visible light look very different in infrared. The large asteroid, with more surface area, radiates more heat and appears brighter in infrared. This means NEO could determine asteroid sizes much more accurately than optical surveys, and it wasn't biased toward bright asteroids. NEO was also observing from space, which gave it access to regions of the sky that ground-based telescopes struggle with, particularly closer to the Sun's direction. During its operational lifetime, NEO discovered over 200 previously unknown near-Earth asteroids and observed hundreds of thousands of asteroids in total, providing size and albedo data that has been invaluable for characterizing the near-Earth asteroid population. But NEO had limitations. It was operating in an orbit that was gradually decaying, bringing it closer to Earth's atmosphere. The increasing atmospheric drag heated the spacecraft and degraded its infrared sensors over time. The mission was extended repeatedly as engineers found ways to keep it operating, but the end was inevitable. In 2024, after more than a decade of bonus operations beyond its designed lifetime, NEO was finally retired. Its orbit had decayed to the point where atmospheric drag made stable operations impossible, and the spacecraft was allowed to re-enter Earth's atmosphere. The loss of NEO leaves a significant gap in our asteroid detection capabilities. We no longer have a dedicated infrared space telescope scanning for near-Earth asteroids. We're back to relying primarily on ground-based optical surveys with all their limitations. The good news is that NASA has plans for a replacement. The Near-Earth Object Surveyor, or NEO Surveyor, is a space-based infrared telescope specifically designed for asteroid detection and characterization. NEO Surveyor will operate from the Sun-Earth L1 Lagrange point, a gravitationally stable location about 1.5 million kilometers from Earth in the direction of the Sun. This vantage point will give NEO Surveyor an unobstructed view of the inner solar system, allowing it to detect asteroids that approach from the direction of the Sun, the blind spot that plagues ground-based surveys. The mission's infrared telescope will be optimized for detecting the thermal emission from asteroids, making it highly effective at finding dark carbonaceous asteroids that are difficult for optical surveys to detect. NASA's goal for NEO Surveyor is ambitious: to discover 90% or more of near-Earth asteroids larger than 140 meters within a decade of operations. Current surveys have found about 40%. NEO Surveyor is meant to close that gap, to finally give us a comprehensive census of the potentially hazardous asteroid population. The spacecraft will scan large swaths of sky, detecting asteroids as they move against the background of stars. Its infrared sensitivity will allow it to detect relatively small asteroids at great distances. Computer algorithms will analyze the data in near real time, identifying new asteroids and calculating preliminary orbits. Follow-up observations, both from NEO Surveyor itself and from ground-based telescopes, will refine those orbits and assess whether each newly discovered asteroid poses any threat to Earth. The mission promises to be transformative for planetary defense. With NEO Surveyor operational, we could finally have the comprehensive early warning system that we currently lack. But there's a catch. As of 2024, NEO Surveyor is still in development. The mission has faced budget pressures and schedule delays. The current launch date is targeted for 2027, though that could slip further. And the mission has a price tag exceeding $1.2 billion, which in the context of government budgets always subject to political pressures and competing priorities, is far from guaranteed. There have been proposals to cancel or significantly delay NEO Surveyor to redirect funding to other priorities. Some argue that with no imminent known threat, spending over $1 billion on asteroid detection isn't urgent. This is, to put it mildly, short-sighted. The entire point of planetary defense is to find threats before they become imminent. Once an asteroid is only months or years away from impact, our options for dealing with it become extremely limited. But if we detect a potentially hazardous asteroid decades in advance, we have time to characterize it properly, to refine its orbit, and if necessary, to plan and execute a deflection mission. NEO Surveyor isn't just a nice-to-have science mission. It's a crucial component of defending Earth from a threat that we know for certain exists. The question isn't whether an asteroid will threaten Earth in the future. The question is when, and whether we'll have sufficient warning to do anything about it. Every year we delay launching NEO Surveyor is another year we're flying blind, another year where a city-killer asteroid could be approaching from our blind spot without us knowing. While we wait for NEO Surveyor, the work of asteroid detection continues with existing resources, and some of it is coming from unexpected places. Amateur astronomers and citizen scientists have been making significant contributions to asteroid discovery and characterization. Projects like Asteroid Zoo, which closed in 2017 but was succeeded by similar initiatives, allowed volunteers to examine telescope images and identify potential asteroids that automated algorithms might have missed. Thousands of people around the world participated, reviewing images from professional surveys and flagging objects that warranted follow-up observation. Several near-Earth asteroids were discovered or confirmed through these citizen science efforts. The involvement of amateur astronomers in asteroid detection has a long history. Many significant asteroids have been discovered by dedicated amateur astronomers using relatively modest telescopes. What amateurs lack in equipment size, they often make up for in observing time and persistence. Professional survey telescopes have enormous data analysis pipelines to manage, and some objects inevitably slip through. Amateur observers, often focusing on specific regions of sky or specific types of observations, can catch things the big surveys miss. More recently, artificial intelligence and machine learning have begun revolutionizing asteroid detection. Traditional detection algorithms work by comparing multiple images of the same region of sky and looking for objects that moved. This works well, but it requires relatively clean data and can miss faint objects or objects in crowded star fields. Machine learning algorithms can be trained on thousands of examples of known asteroids and then applied to telescope data to identify potential asteroids even in challenging conditions. These AI systems can process data much faster than human reviewers and can often detect fainter objects than traditional algorithms. Several research groups have developed machine learning models that can process archival telescope data, images taken years ago for other purposes, and identify asteroids that were present in the images but were never recognized at the time. This has led to the discovery of near-Earth asteroids that were literally hiding in plain sight, captured by telescopes years ago, but only now identified through the application of modern AI analysis techniques. One particularly interesting application of AI is in predicting which asteroids might be hazardous based on incomplete observations. When an asteroid is first discovered, we often only have a few nights of observations, which gives us a very preliminary and uncertain orbit. AI systems trained on the orbital properties of thousands of known asteroids can analyze these preliminary orbits, and FLAG, which newly discovered asteroids are most likely to be near-Earth asteroids that warrant immediate follow-up observations. This helps prioritize observing time, ensuring that potentially hazardous objects don't get lost before we can determine their orbits precisely. Despite these technological advances and the dedicated efforts of astronomers around the world, the fundamental problem remains. We have found only a fraction of the potentially hazardous asteroids out there. Current statistical models based on the population of asteroids we have discovered and assumptions about how complete our surveys are suggest there are approximately 25,000 near-Earth asteroids larger than 140 meters. We've found roughly 10,000. That leaves 15,000 undiscovered asteroids, any one of which could cause a regional catastrophe if it hit Earth. For smaller size ranges, the numbers get even more sobering. There are probably hundreds of thousands of near-Earth asteroids in the 30 to 100 meter size range, objects comparable to the Chelyabinsk meteor or the Tunguska impactor. We've detected only a tiny fraction of this population. These objects aren't large enough to threaten human civilization, but they're more than large enough to devastate a city. A 50-meter asteroid impacting a major metropolitan area would kill hundreds of thousands of people and cause hundreds of billions of dollars in damage. And we have essentially no warning capability for objects this size. They're simply too small and too dark to be reliably detected by current surveys until they're very close to Earth, potentially too close to do anything about. This is the uncomfortable reality of our current situation. We've made tremendous progress over the past few decades. The number of known near-Earth asteroids has increased from a few hundred in the 1990s to over 35,000 today. We've found most of the planet killers. We've significantly improved our ability to calculate asteroid orbits and predict future close approaches. We've even demonstrated, as we'll discuss later, that we can actually deflect an asteroid if we need to. But we're still vulnerable. We still have massive blind spots in our detection capabilities. We still haven't found the majority of asteroids large enough to cause regional catastrophes. And we're still relying primarily on ground-based optical surveys that have fundamental limitations we cannot overcome without moving sensors into space. The asteroid threat isn't a distant, abstract problem. It's a clear and present danger that we're only partially monitoring. Every day that passes without a comprehensive space-based detection system like NEO Surveyor is a day we're taking an unnecessary risk with the future of human civilization. Understanding the asteroid threat requires understanding how size translates into danger, and the relationship isn't linear or intuitive. A small change in diameter can mean an enormous change in destructive potential, and the frequency with which asteroids of different sizes hit Earth varies by orders of magnitude. Let's work our way up the scale, from the asteroids that hit us regularly but rarely make headlines, to the civilization-ending monsters that thankfully strike only once every few million years. At the small end of the scale, we have objects around 10 meters in diameter. These are roughly the size of the Chelyabinsk meteor, and they hit Earth more often than most people realize. Statistical models based on the observed population of near-Earth asteroids and the cratering record on the Moon suggest that 10-meter asteroids impact Earth approximately once every 50 to 100 years. That might sound infrequent, but it means there's a decent chance of one or more such impacts happening in your lifetime. The Chelyabinsk event in 2013 was exactly this type of impact. The asteroid was roughly 20 meters in diameter, which is actually on the larger end of this size class. It entered Earth's atmosphere at approximately 19 kilometers per second, which is fairly typical for asteroid impacts. As it plunged through the atmosphere, friction and ram pressure from the compressed air in front of it heated the asteroid to extreme temperatures. At an altitude of about 30 kilometers, the thermal stress caused the asteroid to fragment catastrophically. The explosion released approximately 500 kilotons of energy, about 30 times the yield of the Hiroshima atomic bomb. For comparison, the largest nuclear weapon in the current U.S. arsenal, the B-83, has a maximum yield of 1.2 megatons, only about twice the energy of the Chelyabinsk explosion. So this relatively small asteroid, something you could park a few cars on if it were sitting on the ground, exploded with roughly the force of a strategic nuclear weapon. Fortunately, it exploded at high altitude. If the same object had been structurally stronger and survived deeper into the atmosphere before fragmenting, or if it had been made of iron rather than stone, it could have reached the ground largely intact. A 20-meter iron asteroid impacting at 19 kilometers per second would penetrate through the atmosphere and strike the surface with most of its kinetic energy intact, creating an explosion of similar magnitude but at ground level rather than 30 kilometers up. The devastation would have been far worse. As it was, the high-altitude airburst at Chelyabinsk damaged over 7,000 buildings and injured more than 9,500 people, mostly from flying glass. If it had exploded over a major city center, or if it had impacted the ground, we could have been looking at casualties in the tens of thousands. The truly sobering fact about this size class is that we detect almost none of these objects before impact. The Chelyabinsk meteor was not detected by any survey telescope before it hit. The 2008 TC3 asteroid, which was detected about 20 hours before it impacted Sudan, remains the only asteroid that was detected before atmospheric entry. And it was only spotted because it happened to pass through a region of sky that a survey telescope was observing at just the right time. For every other 10-meter class impact in recorded history, the first warning was the fireball in the sky. Current detection systems simply cannot reliably find objects this small until they're very close to Earth, by which point it's too late to provide meaningful warning or take any protective action. Most 10-meter asteroids explode over oceans, simply because oceans cover 70% of Earth's surface. These events often go unnoticed except by military satellites that monitor for nuclear weapons tests and can detect the characteristic flash of an asteroid airburst. Analysis of this satellite data has revealed that small asteroid airbursts happen far more frequently than most people realize, with objects a few meters across exploding in the upper atmosphere several times per year. Most of these are too small and too high altitude to cause any damage or even be noticed from the ground. But they're a reminder that we're constantly being bombarded by space debris. Moving up in size, we come to the 50 to 100 meter class, and this is where things get significantly more dangerous. The canonical example of an impact in this size range is the Tunguska event of 1908. On the morning of June 30th, 1908, an asteroid or comet estimated to be between 50 and 80 meters in diameter entered Earth's atmosphere over Siberia. It exploded at an altitude of 5 to 10 kilometers above the remote Tunguska region with a force estimated at 10 to 15 megatons of TNT. The explosion flattened approximately 2,000 square kilometers of forest, knocking down an estimated 80 million trees in a radial pattern centered on the blast. The shock wave was recorded on seismographs around the world. People reported seeing the fireball and feeling the heat from the explosion hundreds of kilometers away. If you had been standing at ground zero beneath that airburst, you would have experienced thermal radiation intense enough to cause third-degree burns, followed milliseconds later by a shock wave traveling faster than the speed of sound that would have killed you instantly. Fortunately, the Tunguska region in 1908 was essentially uninhabited. The few indigenous Evenki people in the area reported being knocked off their feet by the blast wave, and some of their reindeer were killed, but there are no confirmed human fatalities. If the same asteroid had arrived 4 hours and 47 minutes later, Earth's rotation would have positioned St. Petersburg, then the capital of the Russian Empire, with a population of over 1.5 million people, directly under the impact point. The entire city would have been devastated. hundreds of thousands of people would have died. It would have been the deadliest single disaster in human history up to that point. The difference between an amusing historical footnote about some trees falling down in Siberia and a catastrophe that might have changed the course of the 20th century was less than 5 hours of Earth's rotation. Tunguska-class impacts are estimated to occur approximately once every 1,000 to 2,000 years. That means there's roughly a 5 to 10% chance of one happening in the 21st century. Given that roughly 50% of Earth's land area has population densities high enough that a Tunguska-scale airburst would cause significant casualties, and accounting for the additional 70% of Earth covered by oceans where an impact would still cause problems through tsunamis if the asteroid was large enough, the probability of a Tunguska-class impact causing a major disaster sometime in the next century is genuinely concerning. We've cataloged only about 30% of near-Earth asteroids in the 50 to 100 meter size range. That means roughly 70% of objects capable of causing Tunguska-scale devastation are completely unknown to us. One could be heading toward Earth right now, scheduled to arrive next year or next decade, and we might not know about it until it's too late to evacuate the impact zone. Even with evacuation, a Tunguska-scale impact on a major city would be catastrophic. You can evacuate people, but you can't evacuate the infrastructure. Imagine the explosion happening over Manhattan or London or Tokyo. Even if the entire population was successfully evacuated, which would be a logistical nightmare requiring days or weeks of advance warning, you'd still lose one of the world's major economic centers. Buildings would be destroyed or heavily damaged across hundreds of square kilometers. The economic impact would be in the trillions of dollars. And that's assuming we had enough warning to evacuate, which with current detection capabilities, we probably wouldn't. Stepping up another level in size, we reach the 140 to 300 meter class. This is what planetary defense experts call the city killer range, and it's where the threat becomes truly terrifying. An asteroid 200 meters in diameter impacting Earth would release energy equivalent to several hundred megatons of TNT. If it hit a populated area, it would obliterate everything within tens of kilometers of the impact point. The blast wave would cause severe damage to structures hundreds of kilometers away. If it impacted an ocean, the resulting tsunami would devastate coastlines across an entire ocean basin. The reason planetary defense programs have focused on the 140-meter threshold is that this represents a rough boundary where asteroid impacts transition from being local or regional disasters to being potential civilization-threatening events. An asteroid smaller than 140 meters can cause enormous damage, but the effects are geographically limited. An asteroid larger than 140 meters starts to have continental or even global effects through secondary consequences like climate disruption and economic collapse. Impacts in this size range are estimated to occur roughly once every 10,000 to 20,000 years. That sounds comfortably infrequent, but probability doesn't work on a schedule. The fact that we're statistically due for one every 15,000 years on average doesn't mean we get 15,000 years of safety followed by an impact. We could have one tomorrow, we could have two in the same century, or we could go 50,000 years without one. The randomness is part of what makes this threat so difficult to manage psychologically and politically. We know the threat exists. We know roughly how often impacts occur. But we don't know when the next one will happen, which makes it hard to maintain funding and political will for detection and deflection programs. As of 2024, we've discovered approximately 10,000 near-Earth asteroids larger than 140 meters. Current estimates suggest there are about 25,000 such objects in near-Earth space. We've found 40%. The remaining 60%, roughly 15,000 asteroids, are out there somewhere, and any one of them could cause a regional catastrophe. To put that in perspective, we've found fewer city-killer asteroids than there are Starbucks locations worldwide. The statistical probability that one of those undiscovered asteroids is on a collision course with Earth in the next century is actually not that low. Moving into the 500 to 1,000 meter size range, we enter the realm of continental devastation. These impacts would cause effects that extend far beyond the immediate impact region. An asteroid 500 meters across, roughly the size of Bennu, would release energy equivalent to thousands of megatons. The impact crater would be enormous, 10 kilometers or more in diameter depending on the asteroid's composition and impact velocity. Everything within hundreds of kilometers would be destroyed by the initial blast. The seismic shaking would be detected globally and would be powerful enough to trigger earthquakes along tectonic fault lines far from the impact site. But the immediate blast effects, as terrible as they would be, wouldn't be the worst of it. The long-term consequences would threaten billions of people. When an asteroid this large impacts Earth, it excavates an enormous amount of material and throws it high into the atmosphere. Some of this material escapes the atmosphere entirely and falls back to Earth over a period of hours or days. As this debris re-enters the atmosphere at high velocity, it heats up from friction, and this thermal radiation can ignite fires across vast areas. There's evidence that the dinosaur-killing impact 66 million years ago created thermal radiation intense enough to ignite fires globally as the ejected material re-entered the atmosphere. Even a much smaller impact by a 500-meter asteroid would likely start fires across an area the size of a continent. The dust and soot from these fires, combined with the dust from the impact itself, would be lofted into the stratosphere where it would spread globally. This dust would block sunlight, causing what's called an impact winter, a period of reduced sunlight and lower temperatures that could last for years. The agricultural consequences would be catastrophic. Global crop failures would lead to famine. Supply chains would collapse. Even regions far from the impact that suffered no direct damage would face starvation as food supplies dwindled. The death toll from these secondary effects could easily reach into the billions. An impact in the ocean would be equally catastrophic, just in different ways. A 500-meter asteroid hitting the Atlantic Ocean would generate tsunamis that would be tens or even hundreds of meters tall when they reached coastlines. The entire Atlantic Rim, from North and South America to Europe and Africa, would be devastated. Every coastal city would be destroyed. Hundreds of millions of people would be killed in the hours following impact. And again, the long-term economic and agricultural consequences would affect the entire world. We have a much better handle on asteroids in this size range. Objects 500 meters and larger are easier to detect because they're brighter and can be seen from greater distances. NASA estimates we've found approximately 70 to 80% of near-Earth asteroids larger than 500 meters. That still leaves several hundred undiscovered, but the situation is far better than it is for smaller objects. The Barringer crater in Arizona, also known as Meteor Crater, provides a vivid example of what even a relatively small object in this category can do. The crater is 1.2 kilometers in diameter and 170 meters deep. It was created approximately 50,000 years ago by an iron asteroid estimated to have been only about 50 meters in diameter. Iron asteroids are much rarer than stony asteroids, but they're also much more dangerous because they're stronger and denser. A 50-meter iron asteroid carries more kinetic energy and is more likely to survive atmospheric entry intact than a 50-meter stony asteroid. The Barringer impactor struck with energy estimated at 10 to 20 megatons, similar to the Tunguska explosion, but because it was iron rather than stone, it reached the ground instead of exploding in the air. The result was a massive crater that remains prominently visible 50,000 years later. If a similar impact occurred today near a populated area, the death toll would be in the hundreds of thousands. The crater would obliterate everything within several kilometers of the impact point. Finally, we reach the threshold that defines the true nightmare scenario. Asteroids 1 kilometer and larger. This is the size where we start talking about mass extinction events, the end of civilization, and potential extinction of the human species. An asteroid 1 kilometer in diameter impacting Earth would release energy equivalent to roughly 100,000 megatons of TNT, about 20 times the total explosive yield of all nuclear weapons in existence. To put that in perspective, during the Cold War, the combined nuclear arsenals of the United States and Soviet Union peaked at approximately 60,000 megatons. A single 1-kilometer asteroid impact would release more energy than humanity's entire nuclear arsenal detonated simultaneously. The impact crater would be 20 kilometers or more in diameter. The blast wave would cause severe damage out to distances of hundreds of kilometers. Depending on where it hit, it might trigger volcanic eruptions by fracturing the crust, or trigger massive earthquakes, or generate tsunamis that would cross entire ocean basins. But again, these immediate effects, as catastrophic as they would be, pale in comparison to the long-term global consequences. The dust thrown into the atmosphere by a 1-kilometer impact would block sunlight globally for years. Photosynthesis would essentially stop. Temperatures would plummet. This impact winter would be far more severe than anything a smaller asteroid could cause. Agriculture would become impossible across most of Earth. Even with modern technology and food storage, human civilization would face collapse. The global population, currently around 8 billion, would plummet as food supplies ran out. Billions would die. Governments would collapse. The survivors would be scattered remnants trying to endure in a dark, cold world until the dust settled and the sun returned. This is not hyperbole. This is the scientific consensus on what a 1-kilometer impact would do based on climate modeling and our understanding of atmospheric physics. The worst-case scenario, an impact by an asteroid significantly larger than 1 kilometer, enters the realm of true mass extinction. The dinosaur-killing asteroid that struck the Yucatan Peninsula 66 million years ago was approximately 10 kilometers in diameter. It released energy estimated at roughly 100 million megatons, about 1 million times more powerful than the largest nuclear weapon ever tested. The impact created the 180-kilometer-wide Chicxulub crater, triggered global firestorms, generated mega-tsunamis, caused massive volcanic eruptions, and threw so much dust into the atmosphere that sunlight was blocked for years or possibly decades. About 7% of all species on Earth went extinct, including all non-avian dinosaurs. If a similar impact happened today, it would be the end of human civilization and quite possibly the end of humanity itself. The good news, and we should focus on the good news here because it's important, is that we've found approximately 95% of near-Earth asteroids larger than 1 kilometer. Out of an estimated 900 to 1,000 such objects, we've discovered about 860. None of the ones we've found are on collision courses with Earth for at least the next century. The remaining undiscovered planet killers, perhaps 30 to 40 objects, are out there somewhere. But the fact that we haven't found them after decades of systematic searching suggests they're probably in orbits that don't bring them close to Earth very often. There's always a chance that gravitational perturbations, perhaps from a close encounter with Jupiter or another planet, could alter one of these orbits and send a previously safe asteroid onto a collision course with Earth. But such orbital changes are rare and unpredictable. For practical purposes, the planet killer threat is the one we've actually managed to get mostly under control. The threat that keeps asteroid researchers awake at night isn't from the massive civilization-ending rocks. We've found most of those. It's from the city killers and regional devastators in the 140-meter to 1-kilometer range. These are large enough to cause catastrophic damage and kill millions of people, but small enough that we've only found a fraction of them. And the painful irony is that these are also the size range where deflection would be most practical if we had enough warning. A 200-meter asteroid is far easier to deflect than a 1-kilometer asteroid, requiring much less energy to change its orbit enough to make it miss Earth. But we can only deflect asteroids we know about, which brings us back to the fundamental problem: detection. We need to find these objects decades before they threaten us, while we still have time to do something about them. The size-danger relationship also interacts with impact location in important ways. An asteroid's destructive potential varies enormously depending on where it hits. A 200-meter asteroid impacting the Sahara Desert would be catastrophic for anything within the immediate blast radius, but the long-term global consequences would be relatively limited. The same asteroid, impacting the Atlantic Ocean between Europe and North America, would generate tsunamis that would devastate the world's most heavily populated and economically important coastlines. The death toll and economic damage would be orders of magnitude higher. Similarly, an impact in a densely populated region like South or East Asia would directly kill far more people than an impact in a sparsely populated region, even if the impact energy was identical. This geographic variation means that the average impact of a given size might kill a certain number of people, but individual impacts could be much more or much less deadly depending on location. It's a cosmic lottery where the stakes vary depending on where the dice land. There's also the question of impact angle. Most presentations of asteroid impacts assume a vertical or near-vertical impact, where the asteroid is traveling more or less straight down when it hits. But orbital mechanics means that most impacts actually occur at oblique angles, with the asteroid striking the surface at 30 to 45 degrees from horizontal. Oblique impacts distribute energy differently than vertical impacts. They create elliptical rather than circular craters, and they tend to throw more ejecta in the downrange direction. For airburst events, the angle of entry affects the altitude at which the asteroid breaks up, which in turn affects the area over which the blast effects are distributed. A low-angle entry might allow an asteroid to penetrate deeper into the atmosphere before fragmenting, or might cause it to skip off the atmosphere like a stone skipping across water. These details matter enormously for predicting the consequences of a specific impact, but they're difficult to calculate without knowing the precise trajectory of the incoming asteroid. This is why impact risk assessment is as much about probability as it is about physics. We can calculate the general consequences of a 300-meter asteroid impact, but the specific effects of any particular impact depend on dozens of variables, many of which we can only determine once we've detected the asteroid and calculated its trajectory precisely. The fundamental lesson from looking at the size-danger matrix is this: small asteroids hit often but cause localized damage. Large asteroids hit rarely but cause global catastrophe. And the middle range, the city killers, represent the sweet spot of danger where impacts are frequent enough to be a real concern within human timescales, but large enough to cause catastrophic damage. This is the size range we need to focus on detecting, and it's the size range where our current detection capabilities are most inadequate. Every year, we delay implementing a comprehensive detection system like NEO Surveyor is a year we're gambling that one of those 15,000 undiscovered city killers isn't heading our way. So, what would actually happen if we detected an asteroid on a collision course with Earth? The answer depends critically on the size of the asteroid and where it impacts, but we can walk through the most likely scenarios based on our understanding of impact physics and the historical record preserved in Earth's geology and in observations of impacts on other bodies in the solar system. Let's start with the most probable scenario: an ocean impact. Oceans cover approximately 70% of Earth's surface, which means any randomly arriving asteroid has about a 70% chance of hitting water rather than land. This might seem like good news at first. Water can absorb energy, And there's a common misconception that an ocean impact would be less dangerous than a land impact because the water would cushion the blow. Unfortunately, the reality is far worse. When a large asteroid enters Earth's atmosphere at typical impact velocities of 15 to 25 kilometers per second, it's moving so fast that, from the asteroid's perspective, even air behaves almost like a solid. The atmosphere doesn't have time to get out of the way. It compresses in front of the asteroid, heating to extreme temperatures and creating a brilliant fireball visible for thousands of kilometers. For asteroids larger than about 100 meters, atmospheric friction has minimal effect on slowing them down. They punch through the atmosphere in seconds and hit the surface with most of their cosmic velocity intact. When a 200-meter asteroid traveling at 20 kilometers per second hits the ocean, it doesn't splash. At these velocities, water doesn't have time to behave like a liquid. It acts more like concrete. The asteroid's kinetic energy, half its mass times velocity squared, is released essentially instantaneously. For a 200-meter stony asteroid, we're talking about energy in the range of 500 to 1,000 megatons of TNT equivalent, depending on the exact impact velocity and the asteroid's density. The impact creates a rapidly expanding cavity in the water. The ocean is literally pushed aside by the force of the explosion. Within milliseconds, a crater forms that extends down to the seafloor if the impact is in shallow water, or creates a temporary cavity kilometers deep if it's in deep ocean. The water that was displaced has to go somewhere, and it goes outward and upward. But this initial splash, dramatic as it would be, isn't the main danger. The real threat comes from the tsunami generated by the impact. When that asteroid hits the ocean, it transfers enormous momentum to the water. The initial cavity collapse creates a series of waves that propagate outward from the impact site in all directions. These aren't like the wind-driven waves you see at the beach. They're more like the waves generated by underwater earthquakes, except far more powerful. A 200-meter asteroid impacting the Atlantic Ocean would generate waves that could be 100 meters tall or more near the impact site. As these waves travel outward, they carry enormous energy. Tsunami waves in deep ocean travel at speeds of 700 to 900 kilometers per hour, as fast as a commercial jet. They have wavelengths measured in hundreds of kilometers, meaning the distance from one wave crest to the next can be longer than entire countries. In deep water, these waves might only be a few meters high, making them almost invisible to ships at sea. But as they approach coastlines and the water gets shallower, the waves slow down and pile up, growing to enormous heights. The physics of tsunami generation from asteroid impacts is complex and depends on many factors, including the impact angle, the water depth at the impact site, and the asteroid's size and velocity. But computer simulations and scaled experiments give us a good idea of what to expect. For a 200-meter impact in the mid-Atlantic, waves reaching the North American coast would arrive within about 3 to 5 hours depending on the exact impact location. The waves hitting the European and African coasts would take similar times. When these waves reach shore, they wouldn't look like the dramatic breaking waves you see in disaster movies. Tsunami waves are more like an incredibly rapid and powerful rising of the entire ocean. The water level rises by tens of meters in minutes, flooding inland with irresistible force. Everything in the path of the water is swept away: buildings, vehicles, people, entire infrastructure. The force of the moving water is sufficient to demolish reinforced concrete structures. Ships in harbors are picked up and carried inland. When the water recedes, it drags the debris back out to sea, along with anyone who didn't reach high ground in time. For a significant Atlantic impact, every major coastal city on both sides of the ocean would be devastated. Boston, New York, Philadelphia, Miami, London, Lisbon, Lagos, Rio de Janeiro, all would be hit by waves potentially 20 to 50 meters high depending on local geography and how far they are from the impact site. The immediate death toll would be in the hundreds of millions. The economic damage would be incalculable, easily tens of trillions of dollars. Global supply chains would collapse. The world's financial system, heavily concentrated in coastal cities, would be shattered. Even regions that weren't directly hit would suffer severe economic consequences as trade networks broke down. And remember, this scenario is for a relatively modest 200-meter asteroid. Scale up to a 500-meter object like Bennu, and the tsunami heights could double or triple. A 1-kilometer asteroid impacting an ocean would generate waves that would fundamentally reshape every coastline they struck. Now, let's consider a land impact, which is less probable, but in some ways even more immediately devastating. When an asteroid hits solid ground at cosmic velocities, all of that kinetic energy is released in a fraction of a second. The impact creates an explosion that excavates a crater and throws material into the air. For a 200-meter asteroid, the crater would be roughly 3 to 5 kilometers in diameter, depending on the impact angle and the properties of the target rock. Everything within about 10 kilometers of the impact point would be vaporized or completely destroyed by the initial blast. The thermal radiation from the impact would be intense enough to ignite fires out to distances of 50 kilometers or more. Anyone with direct line of sight to the fireball within hundreds of kilometers would receive burns from the thermal pulse. Then comes the blast wave, a wall of compressed air traveling outward from the impact site faster than the speed of sound. Within 20 kilometers, the overpressure would be sufficient to obliterate essentially any structure. Reinforced concrete buildings would be reduced to rubble. Out to distances of 50 to 100 kilometers, the blast wave would still be strong enough to collapse most buildings and kill anyone caught in the open. Even at 200 kilometers from the impact, windows would shatter and light structures would be damaged. The seismic shaking from the impact would be detected globally. Near the impact site, ground acceleration would exceed anything experienced in the worst earthquakes. The shaking would trigger landslides and potentially set off earthquakes on nearby fault lines. For a 200-meter impact, these seismic effects would be severe within a few hundred kilometers but would attenuate with distance. Material ejected from the crater, some of it traveling faster than escape velocity, would rain back down over a huge area. Some of this ejecta would be large enough to cause secondary impacts. Rocks the size of cars or small buildings, thrown hundreds of kilometers by the initial explosion, would fall back to Earth and create their own impact craters. The area affected by this ejecta could extend for thousands of square kilometers around the impact site. If the impact occurred in or near a major city, we'd be looking at near total destruction of that city and severe damage extending across an entire region. A 200-meter asteroid hitting, say, the Los Angeles metropolitan area would kill several million people in the immediate blast and fires. The economic damage would exceed $1 trillion. Transportation networks across the western United States would be disrupted. The psychological impact on the nation and the world would be profound. Scale this up to a 500-meter asteroid, and you move from city-scale to region-scale catastrophe. The crater would be 10 kilometers or more in diameter. The blast effects would extend for hundreds of kilometers. The thermal pulse would ignite fires across an area the size of a small country. We'd be looking at tens of millions of immediate casualties if it hit a populated region, and secondary effects that would affect a substantial fraction of a continent. But even a 500-meter impact, devastating as it would be, wouldn't threaten human civilization itself. The effects would be regional, not global. Humanity would survive, rebuild, and continue, though the affected region might take decades or longer to recover. The threshold where impacts become existential threats to civilization is somewhere around 1 kilometer diameter. At this size, you start getting global environmental effects that threaten agriculture worldwide. A 1 kilometer impact would throw so much dust into the stratosphere that sunlight would be significantly reduced for years. The stratosphere is the stable layer of atmosphere above the troposphere where weather occurs. Material injected into the stratosphere can remain suspended for years because there's no rain in the stratosphere to wash it out. This dust would spread around the globe within weeks, creating a phenomenon called impact winter. Temperatures would drop. Photosynthesis would be inhibited. Growing seasons would be shortened or eliminated entirely in many regions. Even areas far from the impact that suffered no direct damage would face agricultural collapse. With modern agriculture producing just enough food for the current population with relatively little excess, a multi-year global reduction in crop yields would lead to widespread famine. The human population, currently around 8 billion, would likely fall dramatically. Some models suggest that a 1-kilometer impact could reduce the global population by 25% or more, not from the direct impact effects, but from famine and the breakdown of civilization that would follow. This brings us to an important point about impact threats. The biggest danger from large impacts isn't the explosion itself. It's the long-term climatic and environmental effects. The dinosaurs weren't killed by the blast wave from the Chicxulub impact 66 million years ago. They died in the years following the impact when ecosystems collapsed and food chains broke down. The impact winter made it impossible for large animals to find enough food to survive. Only small animals with lower food requirements and those that could survive on detritus made it through the extinction event. Humanity, with modern technology and global food storage systems, would have better survival prospects than the dinosaurs did. We can store food. We have greenhouses and indoor agriculture. We could potentially maintain some level of industrial civilization even through a multi-year impact winter. But it would be the greatest challenge our species has ever faced, and there's no guarantee we'd successfully navigate it without civilization collapsing back to pre-industrial levels or worse. The good news, the very good news that we need to emphasize, is that we've found most of the asteroids large enough to cause impact winters and global catastrophes. The 95% completeness for asteroids larger than 1 kilometer means that out of an estimated 900 to 1,000 such objects, we've found about 860 of them. None are on collision courses with Earth for at least the next 100 years. We've looked at the nightmare scenario and confirmed that it's not going to happen anytime soon. The remaining undiscovered planet killers are out there somewhere, but the fact that decades of systematic searching haven't found them suggests they're in orbits that don't bring them close to Earth very often. We can't be absolutely certain that there isn't a rogue 1-kilometer asteroid we've missed that's heading our way, but the probability is very low. The realistic threat is from the smaller city killer and regional devastator asteroids in the 100-meter to 500-meter range. These are large enough to cause catastrophic damage and kill millions of people, but not large enough to threaten human civilization itself. And there are thousands of them we haven't found yet. This is the scenario we need to prepare for. An asteroid 200 or 300 meters across, discovered to be on a collision course with Earth, with anywhere from a few years to a few decades of warning time. What do we do? The answer depends crucially on how much warning we have. If we detect the asteroid decades before impact, we have a range of options. If we only detect it months or years before impact, our options become much more limited. And if we only detect it days or weeks before impact, we can't deflect it at all. Our only option is evacuation if the predicted impact location is on land, or tsunami warning if it's in an ocean. This is why early detection is so absolutely critical to planetary defense. The deflection methods we have available scale dramatically with warning time. Let's start with the deflection method we've actually tested, the kinetic impactor. On September 26, 2022, NASA's DART mission, which stands for Double Asteroid Redirection Test, successfully demonstrated that we can change an asteroid's orbit by ramming a spacecraft into it. The target was Dimorphos, a small moon about 160 meters in diameter orbiting a larger asteroid called Didymos. DART was a relatively small spacecraft, about the size of a refrigerator with solar panels, with a mass of about 570 kilograms. It was equipped with sophisticated navigation systems that allowed it to autonomously guide itself to impact Dimorphos at a closing velocity of approximately 6.1 kilometers per second. The spacecraft hit Dimorphos almost perfectly, just 17 meters from the asteroid's center. The impact released about 11 gigajoules of kinetic energy, roughly equivalent to about 2.6 tons of TNT. That might not sound like much, but it was enough. The collision changed Dimorphos's orbital period around Didymos by about 33 minutes, far exceeding the mission's minimum success criterion of 73 seconds. Follow-up observations from ground-based telescopes and the Hubble Space Telescope confirmed the orbital change. The impact also created a debris tail extending thousands of kilometers from Dimorphos, consisting of dust and small rocks excavated from the impact crater. The European Space Agency's Hera mission, scheduled to arrive at the Didymos system in 2026, will study the impact crater and Dimorphos's internal structure to understand exactly what happened during the DART impact. DART proved the kinetic impactor concept works. If you hit an asteroid hard enough, you can change its velocity, and changing its velocity changes its orbit. The amount of velocity change, called delta V in physics terminology, depends on the mass of the impactor, its velocity at impact, and the mass and composition of the target asteroid. For a given impactor, hitting the asteroid faster produces more delta V. Hitting a smaller asteroid produces more delta V than hitting a larger one, simply because the same momentum transfer affects a less massive object more. The key insight from DART is that you don't need to change an asteroid's velocity by much to make it miss Earth, as long as you do it far enough in advance. Earth is only about 12,700 kilometers in diameter. If an asteroid is going to pass through the space Earth occupies at the same time Earth is there, making the asteroid arrive just a few minutes earlier or later means it will miss. The farther from Earth you deflect the asteroid, the smaller the velocity change needed to create that timing difference. If you deflect an asteroid 10 years before it would have hit Earth, a velocity change of just a few centimeters per second might be sufficient to make it miss. That's the speed of a slow walk. You're not trying to dramatically alter the asteroid's orbit. You're just nudging it slightly so that when it reaches Earth's orbital distance from the Sun, Earth isn't there anymore. But the math changes dramatically if you have less warning time. If the asteroid is only 1 year from impact when you discover it, you'd need to change its velocity by meters per second to make it miss, which requires a much more energetic deflection. And if you only have months of warning, the required velocity change becomes so large that kinetic impactors become impractical. This is why kinetic impactors are the preferred deflection method for scenarios where we have decades of warning. They're relatively simple. We've proven they work, and they can be built and launched with current technology. For a typical 200-meter potentially hazardous asteroid detected 20 years before impact, a spacecraft perhaps 10 times more massive than DART, impacting at similar velocities, would likely be sufficient to deflect it. You might need multiple impactors for larger asteroids or shorter warning times, but the basic technique is straightforward. The main challenge is hitting the asteroid accurately. DART demonstrated autonomous navigation to target, which is essential because the light travel time between Earth and an asteroid makes real-time control impossible. By the time you see where the asteroid is, it's already somewhere else. The spacecraft needs to navigate itself in the final minutes before impact. Another deflection method that's been extensively studied is the gravity tractor. This is a more subtle and elegant approach that doesn't require impacting the asteroid at all. The idea is to position a massive spacecraft near the asteroid, and simply let gravitational attraction between the spacecraft and the asteroid slowly pull the asteroid off course. Gravity is weak, but given enough time, even the tiny gravitational pull of a spacecraft can measurably affect an asteroid's orbit. A gravity tractor mission would involve a spacecraft with the largest possible mass, probably achieved by using ion propulsion to push against the asteroid's gravity while hovering nearby. The ion engines would provide thrust to keep the spacecraft from falling into the asteroid, while the gravitational attraction slowly changes the asteroid's velocity. The advantage of a gravity tractor is that it's predictable and controllable. You can calculate exactly how much the asteroid's orbit will change based on the spacecraft's mass and how long you operate. You can adjust the deflection in real time by changing the spacecraft's position. And there's no risk of fragmenting the asteroid, which is a potential concern with kinetic impactors if the asteroid happens to be a loosely bound rubble pile. The disadvantage is that gravity tractors are slow. You need to operate them for years or even decades to produce meaningful deflection. They only work for scenarios where you have abundant warning time, probably at least 50 to 100 years before impact. For closer-in threats, they're too slow to be useful. Both kinetic impactors and gravity tractors share a common requirement. They work best when applied decades before the predicted impact. They're prevention methods, not emergency responses. If an asteroid is discovered only a year or two before impact, these gentle deflection methods don't work. The required velocity change is too large to achieve with realistic spacecraft masses and impact velocities. This brings us to the controversial option: nuclear deflection. When most people hear about using nuclear weapons on asteroids, they think of the Hollywood scenario from movies like Armageddon, where you drill into the asteroid, plant a nuclear bomb inside it, and blow it up into pieces that miss Earth. This, to put it mildly, is not how nuclear deflection would actually work, and it's probably not what you'd want to do even if you could. Fragmenting an asteroid doesn't eliminate the threat, it just distributes it. Instead of one large impact, you get many smaller impacts. Depending on how the fragmentation works out, this might or might not be an improvement. If you break a 300-meter asteroid into a dozen 50-meter fragments, and those fragments spread out enough that they don't all hit Earth, you've potentially reduced a continent killer to a few city killers. That might be a worthwhile trade-off if you have no other options. But if the fragments don't spread out much, or if some of them are still dangerously large, you've made the problem worse by creating multiple impact sites instead of one. The actual proposed use of nuclear devices for asteroid deflection is called a nuclear standoff burst. Instead of exploding the bomb inside the asteroid, you detonate it some distance away, typically a few hundred meters to a few kilometers depending on the bomb's yield and the asteroid's size. The nuclear explosion releases enormous energy in the form of X-rays and other radiation. This radiation flash heats the surface of the asteroid facing the explosion to extreme temperatures, vaporizing a layer of surface material. That vaporized material expands away from the asteroid at high velocity, and by Newton's third law, this creates a thrust that pushes the asteroid in the opposite direction. It's like a very powerful, very brief rocket engine. The beauty of this method is that it can deliver far more energy to the asteroid than any kinetic impactor. A nuclear device with a yield of 1 megaton exploded near a 200-meter asteroid could change its velocity by meters per second or even tens of meters per second, depending on the geometry. That's enough to deflect even a relatively imminent threat. The downside is complexity, risk, and political considerations. Launching nuclear weapons into space requires international agreements and opens up concerns about the militarization of space. There's also the risk that the nuclear explosion could fragment the asteroid despite being detonated at a standoff distance, especially if the asteroid is a rubble pile with low structural strength. And you have to get the geometry exactly right. Detonate too close and you might fragment the asteroid. too far and you waste most of the energy. But for scenarios where we discover an asteroid only a few years before impact, nuclear deflection might be the only option that can generate sufficient delta V in the available time. NASA and other space agencies have studied nuclear deflection extensively and concluded that it's technically feasible with existing nuclear weapons technology and existing space launch capabilities. We could, if necessary, launch a nuclear deflection mission on relatively short notice. The DART mission has given us confidence in our ability to navigate to and hit an asteroid. Adapting that technology to carry a nuclear device instead of simply being a kinetic impactor would be straightforward from an engineering perspective, though politically and diplomatically complex. There are other more exotic deflection concepts that have been proposed, including using lasers to vaporize surface material and create thrust, painting one side of the asteroid white to change its thermal properties and enhance the Yarkovsky effect, or even attaching rocket engines directly to the asteroid's surface. Most of these are either too slow to be useful for realistic warning timescales or too complex to be practical. The deflection toolkit that we can realistically deploy consists of kinetic impactors for long warning scenarios, nuclear standoff bursts for short warning scenarios, and potentially gravity tractors for very long warning scenarios involving small asteroids. All of these methods share one absolute requirement. We have to know about the asteroid. None of these deflection techniques work if we only discover the asteroid weeks or months before impact. At that point, the closing velocity is too high and the warning time too short for any deflection method to work. Our only option becomes warning and evacuation. If the predicted impact is on land and we have months of warning, we could potentially evacuate the impact zone and surrounding areas. This would save lives but couldn't prevent the destruction of infrastructure and the enormous economic losses. If the predicted impact is in an ocean, we could issue tsunami warnings and evacuate coastal areas, but again, the destruction would be immense. And if we only have days or weeks of warning, even evacuation becomes extremely difficult. Moving millions of people from coastal cities or impact zones requires time, transportation, and places for them to go. The logistics would be nightmarish. This is why planetary defense experts emphasize detection over deflection. Given enough warning, deflection is straightforward with existing technology. Given insufficient warning, deflection becomes difficult or impossible, and we're left with trying to minimize casualties through evacuation. The entire planetary defense enterprise rests on one foundation: finding the asteroids decades before they threaten us. Every dollar spent on detection is far more valuable than a dollar spent on deflection technology, because deflection technology is useless if we don't know what to deflect. This brings us back to NEO Surveyor and the critical importance of launching a comprehensive space-based detection system. NEO Surveyor represents our best chance to find the majority of potentially hazardous asteroids before they become imminent threats. The mission is designed to discover 90% of near-Earth asteroids larger than 140 meters within a decade of operations. That would mean finding about 15,000 new asteroids, most of which pose no threat, but some of which will be on watch lists for future close approaches. Among those 15,000 discoveries will likely be a handful of asteroids that pose legitimate impact threats decades or centuries in the future. Finding them now, while we have decades to plan and execute deflections if necessary, is the goal. The cost of NEO Surveyor, approximately $1.2 billion, needs to be understood in context. That's less than the cost of a single U.S. aircraft carrier. It's a tiny fraction of global military spending or of the economic damage that even a modest asteroid impact would cause. It's insurance for the planet, and it's insurance that we can actually afford. The alternative, continuing to rely primarily on ground-based optical surveys with their inherent blind spots and limitations, means accepting an unnecessary level of risk. We have the technology to find these asteroids. We've proven we can deflect them if necessary. The missing piece is the political will to fund and launch the detection systems we need. This is fundamentally a solvable problem. Unlike many existential risks facing humanity, asteroid impacts are something we can actually prevent if we're willing to invest the relatively modest resources required. We're not helpless in the face of this threat. We have options, we have technology, and we've demonstrated that our deflection techniques work. What we need is comprehensive detection to give us the warning time to use those techniques. The DART mission in 2022 marked a historic milestone. The first time humanity deliberately changed the motion of a celestial object. We proved we can protect Earth from asteroid impacts if we have sufficient warning. Now we need to build the systems that will give us that warning. The asteroids you should worry about aren't the ones we know about. Those are on watch lists, being tracked, with orbits being refined and impact probabilities being calculated. The asteroids you should worry about are the ones we haven't found yet, the ones that could be approaching right now from our observational blind spots, giving us little or no warning before impact. Those are the asteroids that keep planetary scientists awake at night, and those are the asteroids that make NEO Surveyor and comprehensive detection systems not just scientifically interesting, but an absolute necessity for the long-term survival and prosperity of human civilization. The universe has already shown us it will throw rocks at Earth. The geological record is clear on that point. The question isn't whether it will happen again, but when, and whether we'll have sufficient warning to do something about it. For the first time in the 4.5 billion year history of our planet, life on Earth has developed the capability to see these threats coming and to deflect them. We should use it.